Let's talk about this research problem. In studying this experiment, we're going to learn about experiment design and some of the side benefits of using blocking. So we're looking at gazelles. When stalking gazelles, cheetah frequently have a choice between two gazelles close to each other while grazing. A biologist thought that the choice of prey might be affected by the vigilance behavior of the gazelles. She defined vigilance, hold on, pause right here, and realize how important the next statement is. You can ask any questions you want in science, but you're not going to be able to get answers until you define quantities related to your question. In other words, the abstract concept of vigilance has to be related to some meaningful quantity that I can measure. So that's what she's about to do here. She defined vigilance as the percentage of the time that a gazelle had its head in the air, searching for potential predators. She filmed cheetah stalks and analyzed 16 incidents where two same-sex gazelles were within 5 meters of each other. We're going to go back to that highlighted text in a minute. Thus, either could have been chosen as the cheetah's prey. The table below presents the vigilance levels for each of the gazelles and the difference for each pair. Now let's go back to that highlighted phrase, two same-sex gazelles. This is an example of blocking. Remember, we use blocking in experiments to get more precise answers by removing a confounding variable. So what's that again? A confounding variable is a second variable at play, the effects of which we cannot separate from the explanatory variable. It's a confusing variable, that's all it is. Right, so let's get our bearings here. The explanatory variable in this problem is the vigilance behavior. That's what we're looking to use to explain which gazelle gets chased. The confounding variable could be the sex of the gazelle, because the cheetah may also have a preference for males versus females. So if we mix that up in our observations, we won't always know if it was the vigilance that affected the choice or the fact that it was a hunky male. So we separate. Now, that separation, the blocking, gives us another benefit. We can also get information about the difference between the blocks. I can now look at the data and say, wow, I wonder if there's something different between the males and the females. Well, this problem, as stated on the exam, actually never asked about the main research question. It went straight to the secondary question about the male and female differences. So you have to be alert when you're reading these questions. You could be led to what would be the normal first question that someone would ask, but miss the point of the question, which is something secondary, like what we have here. So we are going to look at the primary question. We're going to ignore for a moment what the question on the exam has asked, but we're going to focus on the research question. Let's look at our table. We see we have vigilance measured for the gazelle that's chased and the gazelle that got away. Okay, that was ignored. Now the differences are already done for you. Okay, and we're going to look at the entire column of data, not separating as they have here. We're not going to separate the data in terms of sex. Okay, we're just interested in the difference between the two categories of chased and ignored. So since we're given the differences between these pairs, we're going to treat them like a paired t-test. We're going to treat this like a paired t-test. So our null will be that there's no difference between vigilance of chased and ignored gazelles. So the average would be 0. The alternative hypothesis is that the vigilance of the ignored gazelle is higher than the chased gazelle. So the difference between chased and ignored should be negative, okay? Or less than 0. That's the same thing. Now, if we go to our calculator and work this out, the t-statistic is negative 3.621. And the p-value is very low, 0.001. So it looks like our vigilance does appear to make a difference. So I'm going to pause here, let you get your calculator and see if you can work it out. And I'm also going to show you how to get that answer. So let's start by turning on our calculator. I have my TI-84 here. And we're going to go to Stat. That's the statistics button there. And the Edit tab comes up, the Edit option. We're going to click on that. And as you can see, I've already populated L1. This is where you put in your data. And if I wanted to put in data into any entry, I just start typing and hit enter. Okay. Now you can clear that. Let's go back to Stat and go down to the clear list. Enter. And then select the list that you want to empty. So I'm going to select, I'm going to do second and find the list down here amongst the numbers. You see the blue indications tell you what the lists are. So I'm going to hit list 2, hit enter, and it tells me it's done it. Now I go back to Stat, enter for edit, and there my list 2 is clear, and all the data that I entered earlier is in list 1. Now this data remains in memory and you can use it any way you want. You can do all kinds of things with it. So let's go back to Stat. And then let's go to our tests. Okay, not calculations. That's more things that we can do another time, but we're going to the tests. We're going to do a t-test for one sample. Now, if we have data, we use the data option there. And you see the null is already set for us, but we can change that. Everything here can be specified. So we'll keep it at 0. That's perfect. And then the list is already shown as list 1, but I can change that. Again, just going to the second and then selecting the list that you want to work on. Frequency will stay at 1. Okay, and then we pick your alternate hypothesis here. We need the average of the data set. We believe that it's going to be less than 0, less than the null of 0. And then we calculate. All right, and as you can see, all my numbers are there. So now we know how to get that t-statistic, and we see that we definitely have a strong result. Okay, and I didn't mention it, but it's important to comment on the appropriateness of your test before you start it. And you would look at the data and see that it is normal in shape, or that it doesn't have a lot of it's not skewed and there are no outliers. So it's appropriate to use a t-test. Now, what if we are wrong about the dependence of the samples? Remember, in the paired scenario, we're assuming that the samples, the two samples have meaningful connections, and so they're not independent of each other. Well, maybe there is no important relationship between the gazelles that were grazing together that would affect the results. So let's do this again as a 2-sample t-test. Now, in the 2-sample t-test, if we're assuming independent samples, There's actually more variability in that scenario because we assume that there's more natural variation just due to the fact that the two gazelles are completely random. They're independent of each other. So doing this test again, we get a new test statistic. The t-statistic is negative 2.46. And you can see the p-value is a lot larger. It's 10 times larger than before. So you see that there's inherently more variability built into the two-sample t-test. But thankfully, this definitely supports the alternative hypothesis that the chased gazelles have lower vigilance on average than the ignored gazelles. Both tests agree. So statisticians often do this. They are not married to one interpretation of a problem. They should challenge their assumptions, look at it in different ways. And if the assumptions are debatable or unclear, they should perform the test using different assumptions and present all the results. They usually take the more conservative answer. Now, let's finally look at the secondary question, which was posed on the exam. It compares the vigilance of the males to the females. Now remember, you get that data because of the blocking. So we actually have some extra, this is a bonus question basically because we did the blocking. So we will assume here that the samples of males and females are not related to one another and we'll consider their differences. But wait, do we look at the difference between the chased males and females? Do we look at the data here or here rather? Or do we look at the ignored males and females? I didn't get that instruction. Well, what would make the most sense? If I am asking which sex is most vigilant, females or males, do I want to consider the lazier bunch, which is probably the chased gazelles? Or do I want to consider the most alert bunch? You know, the more athletic? I'm not sure if it sounds like both of them will give me some bias. The lazy set, they could all be very, very slow or not, you know, nonchalant, and they might all be pretty low and similar. The athletic bunch, same thing. They may all be very similar because they are athletic. They're the best, the cream of the crop. I don't know. So I think I want to design it so that I get a typical set. But now how do I figure out which gazelles are the typical gazelles? Randomization to the rescue. We simply take a random set of vigilance scores. We take some athletic, some lazy, some middle of the road. And if we get it for each sex, we get the random data, then we'll have a very good comparison. All right, so I will use all the data for the chase and ignore columns for one given sex, and then compare it to all the data for the other sex. This is a two-sample t-test. So we're looking at the difference between the average vigilance of the males to the females, or vice versa. You can choose which comes first, okay? So the null says there's no difference, and the alternative says the females are more vigilant than the males. And that means that we'd have a negative difference when you compare males to females. So doing this on the calculator, we see the t-statistics for the 8 females and 24 males is negative 0.245. That has a p-value of almost 0.6, okay, 0.595. So very large p-value. There is insufficient evidence to say that the female gazelles are more vigilant than the males. You see that T statistic is just too close to 0. It's not a convincing argument. So one last point to discuss. What would a 95% confidence interval tell us? Well, it would tell us that the true difference between male and female vigilance would lie inside that confidence interval. And we would be right about that interval about 95% of the time. If we repeat this calculation many times. Also, if the interval contains 0, that confidence interval would have a negative end and a positive end, so it contains 0, then there is a chance that there is no difference between the males and the females, right? Because that's an allowed average. The average could be 0. But big asterisk, please pay attention here. The confidence interval does not tell me the likelihood of any particular value being the actual mean. So I don't know how likely it is that the difference really is 0. No, it is not 95% likely. No, that's not at all what that means. The confidence level says we will capture the real mean inside our big window, our big interval, 95% of the time, if we use the method we're using. And we talked about what that method means. It's a combination of things, but let's focus on the statement, this overall statement. So if we take 100 samples using our method and calculate the confidence interval, 5% of the time, our interval will be completely off, not containing the true mean at all. And 95% of the time, our interval will have the true mean somewhere inside. We don't know where. We don't know where. All right. I hope that was helpful.